Last week, we looked at periodic table, where we looked at periodic trends, their physical properties, and we looked at some physical properties such as atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, metallic character, melting and boiling point. So today we are looking at the periodic trends also, but this time around, we are going to look at the chemical properties. On Monday, we looked at their physical properties, where we looked at those trends. Today, we are looking at the chemical properties. And of course, when we're talking about chemical properties, we're actually talking about the reactions and the kind of compounds they form. So periodic trends of chemical properties. We're not going to go into deep, we're just going to look at the factors responsible for the changes in chemical properties down the group. Then we also look at the chemical properties across the period. But first of all, we look at the chemical properties down the group. First here, we have one of the factors that will affect the chemical properties down the group is increase in shielding of outermost shell electrons. Of course, we know that down the group,
you are not doing select. The worst part was that the three people found car before me.
Can you mute yourselves? Down the group, the shielding increases. And because the shielding increases, or what we call the screening effect, the outermost electrons are actually shielded from the innermost electrons or from the nucleus. So increase in shielding of outermost shell electrons is one of the factors that will affect the kind of chemical properties that will be formed. And also increase in metallic nature. Of course, down the group, metallic nature increases. So increase as metallic nature increases, this will also affect the kind of compounds that is formed. We said down the group, there's increase in ionic character of the compounds. Down the group, we are looking at, like if you take, for example, like group 1, group 2, they are all metals. So metallic character will actually increase down the group. Unlike when we look at across the period, this going from metal to amphoteric to metalloid to non-metal. So metallic character actually increases down the group because down the group, there's more ability to give out electrons and there's less ability to attract. So metallic character increases down the group. And also the ionic character of the compounds increases. Because the metallic character increases, they are more metallic. So they will want to combine with the non-metals, so forming an ionic bond. Like your sodium can combine with your chlorine to form an ionic bond. So there's increase in ionic character of the compounds down the group. Because there's increase in metallic character, there's increase in ionic character, we also expect an increase in basic nature of their oxides. Because the metals are actually basic. So if the metallic character increases, ionic character increases, we also expect the basic character of their oxides to increase because basicity increases as metallic character increases. Now we look at the changes across the period, that is from left to right. And this is due to increase in the nuclear charge. As we go across the period from our lecture on Monday, we found out that across the period, nuclear charge increases because you are actually adding electrons on the same shell. And as you are doing this, the number of proton and electron is increasing, so the nuclear pool is actually increasing. So there's a tendency to attract, so the tendency to attract electrons actually increases because of increase in the nuclear charge. And also across the period, the elements become harder to ionize. That means they become harder to lose electrons. As I told you, the metals have more tendency to lose, while the non-metals have more tendency to gain. So, and as we go across the period, we see that we are going from metallic to non-metal. So because we are going to non-metal, it's actually harder for them to ionize, which means that they have less tendency to attract and more tendency they have more tendency to attract and less tendency to lose electron. So that is why the element become harder to ionize. And total, we said that these changes also occur, cause changes in the nature of the hydride. So aside the compounds forming oxides, They can also form hydrides. They can also form chloride. And because of this difference in changes, this is actually what will affect the nature of the hydrides that will be formed. This will also affect the nature of the oxide that will be formed. It will also affect the nature of the chlorides that will be formed. So this is actually what affects the hydride, the oxide, the chloride of the elements as we go across the period. So we have looked at their factors responsible for the chemical properties down the group, and also factors that affect the chemical properties across the period. So this is actually the end of your period for your periodicity, the physical properties, the chemical properties, and their trends. Now, we go on to period 3 elements. We now move over to period 3 elements. We are looking at this period 3 element because it's actually an interesting group. It's actually an interesting period because we have the sodium, which is your alkaline metal. We have your magnesium, which is your alkaline earth metal. We have your aluminum, which is amphoteric, your silicon, your phosphorus, your sulfur, your chlorine, and your argon. Of course, these are non-metals, and your argon is a gas. So we see that for this period 3 element, we have the trends, the complete trends of elements in the periodic table, the metals, the non-metals, and the gas. So your sodium, the metals are actually hard, but they are not as hard as the transition metals. Your sodium is actually hard, but it's soft. As we go on, we see that your sodium can actually be cut with a knife. So this is your sodium, and this is your magnesium. This is the physical nature of the element. This is your magnesium. This is aluminum. This is your silicon. This is your phosphorus. Your phosphorus looks like like your cigarette stick. It's not very strong. It's a little bit soft. This is your sulfur. Your sulfur actually looks like a sawdust. Your chlorine, of course, your chlorine is a liquid, and your argon is a gas. So these are actually the physical states of this period 3 elements. Now we look at their trends too. We look at the trends of this period 3 element across the period. Of course, we are looking from sodium to argon, so it's just across the period. We are not going to look at the trend down the group. It's only across the period. So first, we look at the atomic radius. Because it's just across the period, that is the only trend we are looking at. We already know that across the period, atomic radius decreases across the period due to there's no shielding, there's increase in nuclear charge. And also, ionization energy increases across the period because as the nuclear pool increases, it will be more difficult for you to remove the valence electron. So the nuclear pool is small and there's no shielding. So ionization energy increases across the period. Also, electron affinity increases across the period because electron affinity, the ability to attract electrons. So because the nuclear pool increases, so there's more attraction. So electron affinity increases across the period. Also, electronegativity, of course, you know the electronegativity is the ability to attract. Because the nuclear pool increases, so electronegativity increases across the period. Metallic character, of course, we expect the metallic character to decrease across the period because as we go across the period, covalency increases while metallic character decreases, and also it has more ability to actually attract more than lose electron. Then melting and boiling point. As we go across the period, we are going from metal to non-metal, so we expect the melting and boiling point to also decrease. So metals possesses high melting and boiling point, while non-metals possess low melting and boiling point. So across the period, the melting and the boiling point decreases. So this is actually the trend of physical properties for your period 3 elements. Now we are looking at the chemical properties as we've already talked about the physical properties and the trends. The chemical properties, we are actually looking at the reactions. Whenever we talk about chemical properties, we're talking about reactions and the kind of compounds that are formed. For the first one is reaction with water. The elements of your group 3 elements react with water, but we are going to see some exceptions and the kind of compounds they form. For your sodium can react with cold water to form a very strong alkaline solution, and it's an exothermic reaction. Enormous amount of heat is given off, so forming sodium hydroxide and hydrogen. Now, for magnesium, your magnesium reacts with steam. Your magnesium is more reactive with steam to form the oxide, but it can also react with cold water. Most times when the surface area is increased, so it can react with cold water to form your magnesium hydroxide. Note that the reaction of the metals with water forms hydroxide. Either it can be strong, it can be weak. Of course, we expect the sodium hydroxide to be stronger alkaline solution than the magnesium hydroxide, because as we go across the period, acidity increases while basicity decreases. So that is why we have your sodium hydroxide as a strong alkaline, while your magnesium hydroxide is a weak alkaline. So alkalinity decreases while acidity tends to increase. Now, for the reaction of your magnesium with steam, it forms the oxide. Please note the reaction with steam. Reaction with steam usually form the oxide, while reaction with cold water usually form the hydroxide.
Why did you go to one Abeokuta?
Can we mute ourselves? My God. So your magnesium oxide is ionic. Of course, we know magnesium with oxygen is ionic. The bond is actually ionic because of the difference in electronegativity. And it's basic and is slightly soluble in water. That is for your magnesium. Please note the difference in the reaction with water and steam, and the difference in the formation of the kind of compounds that are formed.
Matric number, name, department. This person puts one, put matric number. Now put GT Bank there. She is not account number. She put matric number. She now put GT Bank. She now put her name.
I don't know why they are disturbing my class. I can't understand. So we go over to aluminium. Aluminium, because it's amphoteric, it will react with acid and base. So aluminium does not actually react with water, but it can react with steam. Also note that the reaction of your aluminium with steam will give us the oxide. Aluminium is not, magnesium and aluminium is not very reactive with water because they usually have this thin oxide film covering it, so it makes it unreactive. But with steam, it will form the oxide, not the hydroxide. So your aluminium oxide is ionic, just like your magnesium oxide, but it's amphoteric. But your magnesium oxide is basic and slightly soluble in water. Your silicon will also react with steam to form your silicon oxide. But your silicon oxide is covalent. Because of the difference in electronegativity between your silicon and oxygen, it is not actually high. That is why you have a covalent compound. And your silicon oxide is acidic. As I told you, as you go across the period, acidity increases while basicity decreases. And your silicon oxide can actually hydrolyze in water. Now, for your phosphorus and sulfur, they don't react with water. Your sulfur is actually, as I showed you the physical nature of your sulfur, is actually like sawdust. Your sulfur is insoluble in water. And for compounds to actually be soluble in water, one, they must have a very strong oxidizing properties like your fluorine, your chlorine. That is why they are soluble in water. They actually have high oxidizing properties. While for the alkaline and the alkaline earth metals, they are easily ionized in water. But your phosphorus and sulfur, they don't possess these characteristics. So your phosphorus and sulfur, they do not react with water. Your chlorine, as I told you, it has a strong oxidizing property. So your chlorine can react with water to form two acids. This is actually called a disproportionation reaction, where your chlorine is actually acting as both an oxidizing agent and as a reducing agent that is going from, it has different, or is exhibiting different oxidation state from 0 to +1 and then -1. So the reaction of your chlorine with water will form your HCl and your hypochlorous acid. Your hypochlorous acid is a weak acid, while your HCl is a strong acid. While the reaction with argon, your argon is a gas, so your argon does not react with water. Now we look at we are done with the reaction with water and the kind of compounds they form and the kind of bond that is formed in the compound, which we looked at. We now look at the reaction with oxygen. Your period 3 elements react with oxygen to form oxides. While the reaction with water, they form hydroxides, and if it's steam, they form the oxide. But reaction with oxygen all form oxide. Your sodium will react with oxygen to form your sodium oxide. And your sodium oxide is actually ionic, or is ionic due to the difference in the electronegativity between the sodium and the oxygen, and it's basic, and it's actually hydrolyzed in water to form your sodium hydroxide. But in excess of your oxygen in the presence of sodium, it will form a peroxide. So the peroxide, where the oxidation state of your oxygen is actually what? -1. So in excess of oxygen, your sodium will form a peroxide. For magnesium, your magnesium reacts with oxygen to form the oxide and is actually ionic and is basic. And it glows with an intense white flame, while your sodium oxide glows with an orange flame. For your aluminium forms also reacts with oxygen to form the oxide and is ionic, but is amphoteric, and it glows with a white sparkle. Your silicon also reacts with oxygen to form your silicon oxide, and the compound is covalent. For you to know compounds that are ionic or covalent, it has to do with difference in electronegativity between the element and oxygen. Your silicon oxide, just like the reaction with steam, is acidic, and it can also hydrolyze in water. Now for your phosphorus, your sulfur, and your chlorine, they all react with water. So all period 3 elements react with oxygen. For your phosphorus reacts with oxygen to form your phosphorus 3 oxide, which is also covalent and acidic because it's a nonmetal. But in excess of oxygen, your phosphorus will form your phosphorus 5 oxide. So phosphorus 5 oxide is only formed in excess of oxygen, just like your sodium peroxide is formed in excess of oxygen. So your sulfur also reacts with oxygen to form your sulfur 4 oxide, which is covalent, is acidic, and also hydrolyzes in water. And it glows with a pale blue flame. Your chlorine also reacts with oxygen to form your dichlorine heptaoxide. So your chlorine reacts with oxygen to form your dichlorine heptaoxide, which is also covalent. Of course, we know we expect it to be acidic and can also hydrolyze in water. But for your argon is a gas, so there's no reaction with oxygen. Now we look at their reactions with chlorine. That is the formation of halides. Your period 3 elements react with chlorine, that is the halide, to form the metal halides. Your sodium can react with chlorine to form our normal sodium chloride, that is our table salt. And due to the difference in the electronegativity also, we expect it to be ionic. Your magnesium, forming your magnesium chloride, is partly covalent. As I told you, covalency increases across the period while metallic character decreases, or ionic character decreases while covalency increases. Your aluminum will also react with your chlorine to form your aluminum chloride. Your silicon will form your silicon chloride. Your phosphorus will form your phosphorus chloride. So for your phosphorus, note we always talk about when it's in excess or when it's normal. So for the excess, excess of chlorine will actually give us the phosphorus 5 chloride, while in the normal range of your phosphorus, we have your phosphorus 3 chloride, and they are all covalent because they are covalent. The elements are covalent, so we expect their compound to also be covalent due to the difference in electronegativity, which is not much. Your sulfur will also form a covalent compound, your sulfur chloride, while your argon, no reaction with chlorine. Your argon is a gas, so it does not react with chlorine. So that is actually the reaction of your period 3 element with oxygen, with water, with chlorine, that is the halide, to form the halide. So please, as I told you, note the type of compounds that are formed and also know the kind of bond that they exhibit. Depending on the kind on the compound, the element, you know if it's going to be in excess or if it's going to be in the normal range to be able to form the different oxidation states of the metal. So we'll now look at diagonal relationship. What do you mean by diagonal relationship? We said diagonal relationship is a relationship within the periodic table by which certain elements in the second period, this is your second period, have a close chemical similarity to their diagonal neighbors in the next group of the third period. So it's usually between elements in the second period and elements in the third period. That is where they because of where they usually have a close chemical similarity. So we usually have a diagonal relationship between lithium and magnesium, beryllium and aluminum, boron and silicon, and so on and so forth. The other should be sulfur and the phosphorus. So now, what are some of the similarities? What are some of the properties that will make elements to show diagonal relationship? As I've told you, we've seen the element that usually show diagonal relationship. What will make this element to show diagonal relationship? One, it can be due to similar size to charge ratio. It can be due to similar, if they have the same size, or they have the same size to charge ratio. Also, if they have similar polarizing power. When we talk about polarizing power, we are talking about the ability to attract and repel. So if they can attract and repel, then if they have that similar power, then they will show what we call diagonal relationship. Also, if they have similar electronegativity. And the pairs of elements that show this diagonal relationship, as I've told you, between lithium and magnesium, beryllium and aluminum, boron and silicon. So your lithium and magnesium usually have similar size to charge ratio. Your beryllium and aluminum most times usually have similar electronegativity. So depending on depending on the property that they have, will actually tell us if such pairs of elements will show diagonal relationship. So now we compare the elements of lithium and magnesium in terms of their diagonal relationship. Now we are going to compare their carbonates, the kind of carbonate they form, their chlorides, their oxides, and the hydration, their hydride ions, the kind of ions they form in hydration. So one, the carbonates. The carbonates of your magnesium and your lithium are insoluble and they decompose on heating. But the carbonates of your group 1 element are usually soluble in water. So what it means is that most elements that show this diagonal relationship, they are usually different from the elements in their group. They are usually show, aside the size, the electronegativity, and the polarizing power, even in the kind of compounds they form. Their compounds also show, their compounds are also different from the compounds of the elements in their group. So for the carbonate, magnesium carbonate and your lithium carbonate are insoluble in water, but the carbonate of your group 1 element are actually soluble in water. So carbonate of other group 1 elements are soluble and do not decompose on heating. But your lithium carbonate, once you heat it up, it usually decomposes easily. Unlike the carbonate of your other group 1 element, they don't decompose easily. So because the carbonate of your lithium decomposes easily, just like the carbonate of your magnesium. So this shows that they actually exhibit diagonal relationship because of their size. They actually, both of them actually have small size and high charge. Now, also their chlorides. Both chlorides are hydrated. That means they contain molecules of water. Unlike the chlorides of the other group 1 element, they are not hydrated. They form anhydrous compounds. So both chlorides are hydrated. That is your magnesium chloride and your lithium chloride are all hydrated. But the chlorides of your group 1 element are not hydrated. They are usually anhydrous. Now the oxides. Both of them react with oxygen to give your simple oxides. To give your simple oxide, what we call the normal oxide, oxidation state of +2. Other group 1 metals, they can give peroxide and superoxides. Peroxide, that is when the oxygen is in oxidation state of -1, while superoxide when the oxygen is in oxidation state of -0.5. But for your, these are for your group 1 elements. But only lithium will form a simple oxide, that is the normal oxide. And it's similar to your magnesium, which also forms the normal oxide. Now for hydration, both your lithium and your magnesium ions are heavily hydrated in solution because of their dense charge. Because of their dense charge in water, they can actually be hydrated. That is why they form hydrate compounds, because of their high charge. So they can actually be hydrated in water, having some molecules of water in their compounds. We are stuck again. I don't know what happened. It has been behaving well. What happened? Sorry, so maybe I should share it again. I don't know why it's stuck again. I'm sorry. I don't know what happened. We are stuck again. Okay. So we just share again. Okay. So we now compare. The next is comparison of your beryllium and aluminium. Why they, in terms of their diagonal relationship, with nitric acid, both metals are passive and will not dissolve in nitric acid. But with alkaline, both dissolve, giving off hydrogen. Both of them are amphoteric, so they can react with both acid and alkalines. And their oxide, both of them, their oxide are amphoteric. Beryllium oxide and aluminium oxide are amphoteric. And also for their chlorides, both Their chloride are electron deficient. That means they want to accept electrons, so they act as Lewis acids. They act as Lewis acids. I don't know why it's we have a problem. I don't know why. So sorry about that. I don't know what the problem is. So we'll now look at the elements of boron and the silicon. So boron and silicon. So in terms of their hydrides, both of them give a variety of unstable hydrides. Unlike the others, that their hydrides are very stable, like your sodium hydride, your potassium, your sodium hydride is stable. But the hydrides of your beryllium and silicon are actually unstable. So that is, and so they actually form what we call the boranes and the silanes. And in terms of their oxides, both are weakly acidic. Their oxides are weakly acidic to form your boric acid and your metasilicic acid. Their oxides are weakly acidic. Now, in terms of their chloride, the chlorides of your boron and your silicon are volatile and will undergo hydrolysis to give an acidic solution, while the chlorides of the other element, of course, like your sodium is a metal, your sodium is ionic and it's not volatile, it's a solid. So the chlorides of your boron and your silicon are volatile and will undergo hydrolysis to give an acidic solution. So these are some of the similarities in terms of the compounds of your elements that show diagonal relationship. That is your lithium and magnesium, your beryllium and aluminum, and your boron and the silicon. So we've looked at each of them, the kind of compounds they form, and why they actually show this diagonal relationship relating to the size or the size to charge ratio, polarizing power, or electronegativity. Any question? Any question? Any question? Can you hear me? Hello, student, can you hear me? Hello? Hello? Student, can you hear me? Are we there? Hello? Okay, so I muted you.
Yes, ma, we can hear you.
Okay,
We can hear you, ma.
Okay,
We can hear you. We can hear you.
any question? Any question?
Yes, ma. Yes, ma.
Okay, ask your questions.
Ma, please, I once read online somewhere that covalency increases down the group and decreases across the period.
How is that possible? How is that possible? Where are you reading? You see, it's not everything you read online that is correct. How can covalency increase down the group? Down the group, the metal what you have down the group, is it not metals? The elements are becoming more metallic. So how will covalency increase, my dear? It's not possible. Metallic character increases down the group, while covalency increases across the period. Because across the period, there's more tendency to attract electrons, while down the group, there's more tendency to give out. Is that correct? Are you okay with that? Hello? Any other question? Any other question?
No, ma.
No other question. Okay. Okay. So I'll put the last lecture on this one, on the LMS. So I'll also put this one on the LMS. Please always check the LMS. So we see.
Okay, ma'am.
So we see on Friday. We see on Friday.
Thank you, ma.
Thank you. Thank you. Thank you.
Yes, ma'am.
Thank you, ma.
Thank you,
Thank you,
ma.
ma.
Thank you, ma.
Ma'am.